Thank you all for coming. Today we have a treat. We have his research expertise in the thermal characterization and reliability of wide bandgap semiconductor technologies and the packaging of organic and flexible electronics. His work is well regarded and has received many accolades. And I have known Sam since I was an undergraduate student, so he's a great teacher as well. Without further ado, please welcome Professor Graham, and we look forward for a seminar. The floor is yours.
Thank you. So I apologize for the technical difficulties. So I know that I've eaten up a lot of time, and so I'm going to move through this to try to get towards the end of the talk, where I think there's some really interesting things in terms of the concept of thermal management and phonons and layered materials and things that we're going to do with ultra-wide bandgap electronics. But I need to build to that point first. And so what I'm going to do is go ahead and get started on the concepts of wide bandgap electronic devices. And so before I get into all of this, there's always fun in collaborating with people. And so you see this big long list, and I have to acknowledge members of my ONR MIRI team, my gallium oxide GAIN MIRI team, and that's mainly the people that are on the list. Tadatomo Suga from the University of Tokyo, who we've done a lot of work with, and really pushing the boundaries of doing what's called heterogeneous integration with bonding. So you'll see a little bit of that work today. And so this is it's a lot of fun when you can get a lot of interesting researchers together and bring together a lot of talent to address complex problems. And so the idea here is to really look at what's the drive for wide bandgap and these ultra wide bandgap semiconductors. And just in a nutshell, what you're seeing, the commonality on this particular slide is the concept of electrification. So electric vehicles, solid state breakers, electric drive systems on cars, on airplanes, on ships. And then in addition to that, when you look at wide bandgap power devices, you can also, let me start with, go through this really quick, and then I'm going to get to RF. So when you start looking at power electronic systems, what's really interesting is that for all of these, you basically have a number of things that these electronics can do. So you may start out with, first of all, looking at load converters. So I may have a motor that is on an AC bus. In that AC bus, I have to change the AC voltage in order to drive that motor. I may have a DC bus, a DC load, so I may have to do some changes in terms of the load converters. I may also have source converters, where now I'm going to change the source. I may go from a DC to an AC from the battery to this bus. I may change from AC generators to DC. So these are the kinds of things that these electronics will do. In addition to that, I may have power distribution converters. So I may have to go from an AC bus to a high voltage DC, and a number of things, low voltage DC to a load. And so a number of things that will happen in all of these that these electronics will do. Now, the main thing that we're looking at is, of course, people are looking at size and weight, reliability and lifetime. We're looking at efficiency. And part of all of this is governed by the temperature of the devices and thermal management. So that's the part that I'm really concerned with, is digging into the thermal aspects of these devices. When we start talking about RF applications, then we can look at radar systems, satellite communications, which is really big, although they're also using optical links now with satellite communications, and then broadband RF. And so all of these are also driven by wide bandgap, and they're looking at ultra wide bandgap materials now. So when you start talking about the thermal management, these are typical things that a mechanical engineer might look at. There's the die, which, you know, this box right here. So this is the die right here. There's wire bonds coming off. This is going to be packaged onto some sort of substrate, and that's going to be put on a base plate. And typically, the base plate may be water cooled, maybe air cooled, and you're going to take the heat out of these devices. That's the typical structure. And so the part that I'm going to talk about today is, for the most part, because of the time, I'm not going to talk about any of this stuff with the typical thing, moving from the die through these layers into the base plate, water cooling. I'm going to talk about the red box right there, where the heat is being generated, and how do we start the thermal management aspects right there with the die. And so when you start looking at the materials of the die, that's one of the typical things you do, is that you start looking at, like for a power switch, what it's basically doing is that it will actually block a voltage when you don't want current to flow. And then it will switch to an on-state position where current will flow. And so you have to move from sort of this idealized state of infinite resistance, of course, there's no such thing, to something that has zero resistance, again, no such thing. And so when you're doing this switch, you're going through a phase where current is starting to flow, the resistance is coming down, and so you get power dissipation during the switch mode. Same thing when you go off. But what we're looking at here is there's a finite resistance when the device is on. And so we call this the specific on-state resistance when we're looking at that. And what you basically see is that now, this bar right here, you're basically seeing that the specific on-state resistance will go down with different materials. So silicon to 4H silicon carbide, to gallium nitride, to beta gallium oxide. So you see that specific on-state resistance theoretically going down. And what that is doing is it's moving with the band gap of the material. And so there's a number of calculations that you could do to show where this is coming from. And so if you look at these figures of merit, the Liga figure of merit, the high frequency figure of merit, the Johnson figure of merit, all of these figures of merit that we can use to ideally calculate or compare materials, they're basically moving up with increasing band gap. So these are just saying that, hey, it makes sense to go to these wider band gap materials. The problem that you have is that when you go from silicon to silicon carbide, the thermal conductivity goes up. And then all of a sudden you see the thermal conductivity going down. And so we still have to handle power, but now I'm penalizing myself by reducing the thermal conductivity. Although these figures of merit say that this is better, it's the way to go. So the question is, can we help the electrical engineers or can we help device engineers take advantage of these other materials, but also deal with the thermal aspects? And so just quickly, I'll try to, because of the time, what we're going to start out with are gallium nitride heterojunction or high electron mobility transistors. And so what you have here is a material where we're going to have a material like aluminum gallium nitride sitting on gallium nitride. This creates what's called a two-dimensional electron gas. This is basically a nice source of electrons that sit right there near that interface. I don't have to dope the material, this forms. And so this gives me my channel where current wants to flow. So the key thing that I want you to remember is that in order to get that two-dimensional electron gas, I have to put two materials together. This interface, or the interfaces that you see here in this structure, can also block or impede heat transfer. So I have to worry about these interfaces, but they're necessary for the creation of these devices. Gallium nitride and silicon carbide, this interface with the two-dimensional electron gas. And so of course, based upon this device architecture, I will have heating right there, the drain side edge of the gate. This is a simulation where you can see the heating occurs right here. And so when I start talking about thermal management, again, I said I'm looking inside the device because this is where the heating begins. And so is there anything that I can do to try to spread out that heat or to try to deal with this? And again, this is gallium nitride. And this is a substrate where I have interfacial thermal resistance. So you can see the large gradient in temperature just because of the resistance of the contact of those two materials. Okay, and so again, just sort of speeding up, this is what you typically do if you're looking at the full system. I'll have a device, I'll have a substrate, heat spreader, heat sink, cold plate. In our group, we look at all of these aspects. And today I'm going to talk about this part right here. Okay, so let's start out with gallium nitride. So remember, I'm going to have a higher thermal conductivity, and as I start increasing band gap, it's going to become more challenging. And so one of the interesting things is that when I showed you the cartoon of gallium nitride and silicon carbide, the crystal structures are not the same. So what I have to do is put a material in between, like aluminum nitride. And so this allows me to sort of grade between this crystal structure, lattice constant, this lattice constant. And so this layer right here can cause thermal resistance. This material right here has a thermal conductivity of about 380 watts per meter K. I can go to diamond, which is about 2,000. But again, I have to put another material in between them in order to get them to grow together or to bond them. And so I have to worry about that particular layer in order to reduce the thermal impedance. So one of the things that we've been doing is saying, is there any way that we can get rid of the aluminum nitride altogether? And so there's a really interesting technique called surface activated bonding. And so this is the things that we're doing with our collaborators in Japan. So I can take gallium nitride and grow it on sapphire. I can take my silicon carbide. I can actually expose them to this ion beam. It activates the surface. It breaks bonds. They become energetic. I can press these together, and lo and behold, they will stick. And then I can use a laser to basically laser liftoff, remove this substrate. And so this gives you a picture right here of this gallium nitride wafer bonded to a silicon carbide wafer. The reason why we did the two like this, it was easier to get the gallium nitride templates in that size. Commercially, they're harder to find at the larger scales. So we can bond these together. And so you can see this can be done at wafer scale. And then what we've done is we've done another cut to only leave behind a very thin layer of gallium nitride, so we can actually do thermal measurements by time domain thermal reflectance through this in order to measure how resistive is that interface. So remember the picture I showed you, we had aluminum nitride, we get rid of it, there's no aluminum nitride here. So the cartoon, you would think I would have gallium nitride, silicon carbide placed together, and that's not what happens. So even though I put nothing in there, the bombardment of the ions makes this surface amorphous. So I still have an interface. I tried to get rid of that amorphous interface, something in the middle. And so I have this. And so what we can do is I can go back and I can try to anneal it. And so if I go through an annealing step after I do the bond, you can see that kind of recrystallizes. You can see the planes here. You see some fuzziness here. What's interesting, and because of time, I'm not going to show you. If you go do a chemical map, what you'll see is that you have argon trapped in these little spots at the interface. So trying to remove that gas that's trapped at the interface, we're not really sure what it does when we do the measurements. It's there. And so I think when we start looking at more of the science of this, should we use a different molecule? And so you'll see why I'm mentioning that a little bit later, because these molecules can potentially help aid the heat transfer across these interfaces. So here's what we see is that if I use a technique called molecular beam epitaxy and grow directly onto silicon carbide. So this is MBE without aluminum nitride. This shows you basically the thermal boundary conductance. So how well does that interface conduct? So that's the best that we've seen in the literature. And you can see our bonding methodology actually matches that. And it's a number of measurements across the sample, changing the sample thickness. And so this is as bonded. When we anneal and we crystallize, you can see that we get this very, very conductive interface, which is good. So someone may say, well, why not just do MBE? Well, there's an aspect of the throughput for commercial aspects. So bonding would be faster, scalable. The other thing is that when I do the direct growth by MBE on silicon carbide, I have more defects. So it's not as good of a crystal quality for making electronics, but the bonding is. And so I can go through that methodology. So I will skip through this. This is basically showing you the numbers, what I just told you on the previous slide. Okay, so that's just showing that I can take one material and I can bond it to another material and have a really good thermal interface. But then I've also taken a material that has really good electronic properties and I've done the bond. So it helps me to separate this. So the other part is I mentioned, well, what about going to diamond? So we've done this work through the DARPA Near Junction Thermal Transport Program. This is a very interesting program where we showed that we could take gallium nitride or silicon carbide, shrink it down by a factor of 3 by putting on diamond, and you don't get a penalty in terms of temperature rise. So that's actually good. I can make these devices smaller, more compact, in more intense heat sources, and I can still dissipate the energy. And so our calculations show that you can potentially go up to a 5x reduction in device size with no penalty. The only issue is that that's a calculation. In real devices, you have real interfaces, and that becomes hard. So how do you go about doing this? How do you go about doing things with diamond? So you start out with gallium nitride grown on your favorite substrate. It could be sapphire, silicon carbide, or silicon. A lot of people use silicon. I will take a carrier wafer, I will bond it. And so when I do that bond, then I can remove that bottom substrate. So now it's just sort of stuck to this carrier wafer. I can take that carrier wafer now and I can grow diamond on the back. So this is called direct growth. We've done a lot of that. That's what the previous study that I just showed you, that's how it's done. And then I remove the carrier wafer. The other way is, of course, we're going to try the bonding. So what happens if I try to take the gallium nitride and I'm just going to take now high quality diamond? One of the things I want you to notice is that these lines on here are different than these, and it's on purpose because I have to nucleate the diamond, so I get really small grains near this interface. Now I can take single crystal diamond, I can take large grain polycrystalline and bond it directly. So the small crystalline diamond has a large thermal resistance, so I can get rid of that. So these are nice things about going through this process. And so then I can just go through the wafer removal, and this is called transfer bond. So remember before I said I had this silicon nitride, this is the amorphous layer. This is what controls that thermal resistance. When I talked about this large delta between the gallium nitride and the diamond itself. And without going through that today, what we have found is that we have to get this layer down to about 3 nanometers in thickness in order to get the really, really high performance. Again, to try to get to the 5x number, it has to be around 3 nanometers in thickness. So what I showed you here is that I can try to bond. And remember, I'm doing the bonding, and I'm showing you the cartoon that there's nothing at the interface. And so can anyone guess what's going to happen in the real picture? Is there going to be something at the interface? Of course. All right, so here we go. So this is the picture. So what we found is that it's hard to bond GaN directly to diamond. We've done a little bit more on this study with a material called gallium oxide bonding to diamond, but let's stick with this study now. So I tried to get rid of the silicon nitride. And what we found is that we could use a very thin layer of silicon deposited inside the chamber and do the activation and bond it, or we could take a silicon containing metal organic species, embed it inside of the ion beam, and it would break some of the hydrogen off. And so you can sort of mix it in and bond the gallium nitride to the diamond. All right. And so these are just some tricks that we had to do to sort of make this glue layer. And so what you see here is, again, this is 4.2 nanometer thickness right here. This is actually a layer of the amorphous material, as well as about 2 nanometers of this silicon-rich layer that's in the middle. So we get down to about 4 nanometers or so inside of this process. And what we have found is that this particular thermal conductance is as good as the best that we have measured in terms of thermal boundary conductance across GaN bonded to diamond. All right, and so this again just shows you that, you know, hey, I can come along, I can now play around with single crystal diamond, I can play around with other materials where I can't grow single crystal on the backside, but I can bond it. And so this is sort of moving the needle towards starting to dissipate this heat, spread the heat out at the chip level before I ever worry about liquid cooling, air cooling. I'm trying to do it right inside of the device. So we've been very lucky in terms of working with people that actually grow wide bandgap semiconductors, and they let us get inside and play with architecture to try to change the dynamics of the heat transfer inside of the devices. So now I'm going to move on to ultra-wide bandgap. So the lessons that we've learned started out with gallium nitride. Now I'm going to go back to this picture. We talked about this earlier. I'm going to go from silicon to silicon carbide to gallium nitride. Now I'm going to do the first one we're going to look at is beta gallium oxide. And then I could do another one that I don't have drawn on here. This is aluminum gallium oxide. So these are, so this algan layer. So these are, again, ultra wide bandgap materials that people are very interested in today to make power devices and RF devices. And so what's really nice about beta gallium oxide is that I told you before that those 2-inch gallium nitride wafers, they're commercially hard to find. Well, since this is an oxide, people can grow this to very large diameters. So the commercial availability is there. But again, the issue that you have is that this material has a very low thermal conductivity. So people have made devices like these algan transistors that actually rival some work that you've seen in gallium nitride. So this is actually good being done in terms of current densities. And you'll see some other work that's coming out in terms of beta gallium oxide as well, that's starting to show some promise. So let's start looking at the issues here. So when I look at gallium nitride, the thermal conductivity is about, for the thin film form, is about 180 watts per meter K. When I go to bulk, I'm around 200 to 220. Now look at the numbers if I go to beta gallium oxide. We're talking about 12, and it's anisotropic. 12, 24 to 27, and 15. So this is the order of magnitude lower. And then if I go to aluminum gallium nitride, it will depend on the amount of aluminum that I have in the material. And so you get this bathtub curve. right here. And so what you're seeing is that this is dipping below 10 watts per meter K. So this is actually worse than beta gallium oxide. But this, again, these figures of merit say that you should push towards these. The other thing that will happen is that sometimes you need to make layered structures. So this is actually a layered structure of gallium oxide, aluminum gallium oxide. And so we start putting all of these interfaces together. Those interfaces can also impede heat transfer. And so we measured this, and you can see this is 3 to 5 watts per meter K. So there are people that throw their hands up and say, well, this is sort of the end of the story. Why go down this road? Let's move to something else. And so we wanted to continue to take a look at what are the things that we could do here in order to enable these devices. So the first thing is to say, let's go back to what we learned before about trying to engineer heat transfer or heat spreading inside of the device. So if I look at this device over here on this side, I have my gallium nitride, gallium oxide type structure. And so I'm going to have heating at the drain side edge of the gate. I will have heat that has to now pass through this gallium oxide material, and it's going to sit on a substrate. I can have a thermal boundary conductance that's sitting right here. And so what you'll see is that if I have a 10 micron thick layer, or if I have a 1 micron thick layer, you can see that as I thin this layer down, the temperature actually drops. Okay, that's expected because I'm reducing the thermal resistance here. So what the other thing that you can see is that this is the substrate thermal conductivity. So it really doesn't matter if I go to, this is 1,000 watts per meter K. It doesn't matter if I go to, you're really not going to get much more of a benefit than if I'm back here at something like silicon carbide. So the other part is that this thermal boundary conductance here is that if I'm at 10 micron thick gallium oxide, it's relatively flat compared to if I go to 1 micron. So then you can see that the thermal boundary conductance really matters when I have thin layers. So really what it's saying is that when this is really thick, this basically dominates the resistance. When I thin this, then this resistance matters. That's basically what we're saying here. And so the other way of looking at this is to say, my heat is being generated right here near the top. Why not pull the heat out of the top? It's a shorter path to get to this substrate going this way than it is this way. And so you may say, well, how do I package this thing so it's on the top? If anyone's ever heard of flip chip packaging, you can actually just flip it over, put this onto a high thermal conductivity substrate, pull it out of that side. The other thing is that this gray material that you see right here plays a large role in terms of helping to pull the heat out. The challenge that we have technically is that this material right here has to be a dielectric. It has to have the right breakdown properties, and it has to also have the right thermal conductivity. So a lot of these underfill materials have good breakdown properties, but they're really, really low thermal conductivity. And so we want to actually push something where you can see where the temperature really starts to drop. So we're talking about 1 watt per meter K. If you can get above 10, then you really have something that could really be integrated into these devices to really help with that heat transfer. And so of course I can also do this where I do double-sided cooling and cool from the top and the bottom. So let's go back to our favorite way of putting these together. So remember I said if I have really thin gallium oxide, then I can put it on a high thermal conductivity substrate. I don't need diamond. And so again, what we're doing here is gallium oxide. This one used a very thin layer of aluminum oxide to help with the bonding. The ion irradiation caused an amorphous silicon carbide layer. So you can see a continuous theme here. I have something that turns into an amorphous layer. And I put this on silicon carbide. And so what you're seeing here is this thermal boundary conductance is around 100 megawatts per meter squared K. And so you can see what we're looking at here is that if I can get up to here, then it starts to flatten out. So we're actually pushing sort of the boundaries of where that technology needs to go in terms of making those devices by doing this bonding. And again, the same thing holds true, that I can do this wafer scale. We've also done some growth with the Naval Research Laboratory where we can grow these together. And so this is slightly, instead of being 100, this is slightly higher, 140 megawatts per meter squared K. So just slightly higher if you do the growth. But again, this throughput of having purchased silicon carbide wafers, purchasing gallium oxide wafers, I can just bond these and start making devices. So one of my, I stole some slides from my former student who's now a professor at Penn State. And so we showed him our results. He actually went and made devices. And so what he's showing here is that if I have gallium oxide on top of a gallium oxide substrate, you can see two measurements of temperature. And so you can see as you take the power up, this is in a term called watts per millimeter, you can see that the temperature is almost reaching 200 C. So getting very, very hot. Now, if he does this, he bonds this to 4H silicon carbide, you can see at the same powers that we're barely getting, we're not even reaching 60 C in terms of temperature. So he shows that, yeah, this is actually going to work if you can actually do this. And so again, wafer scale, you can now take these and make these devices and show that you can really do cooling for this structure. So I'm going to talk about aluminum gallium nitride. I'm going to bring all these things back home as I run to the end. So one of the things that we started looking at here, this is some work being done with Sandia National Laboratories. Again, this hot spot at the drain side edge of the gate. What we're worried about is this aluminum gallium nitride on aluminum gallium nitride. There's an aluminum nitride buffer layer here that they used to grow when they place it on top of sapphire. So sapphire is aluminum oxide. So one of the things that we would like to be able to do is spread the heat. So I can place a heat spreader on top. And so this is a dielectric layer, a heat spreader. And then the other thing that I could do is then do the top side, the flip chip bonding, where I pull the heat out through the top. So there are a couple of different things that you can do. So this is sort of the normal packaging. So remember, let's see, I'll just point out that sapphire has a very, very low thermal conductivity. It's not great. And so the question is, if I just put a heat spreading layer on top, can I actually help and get away with the thermal management for these kinds of devices? So I want to just sort of show you this. I'm not going to walk through these cases. This is a eye chart. This is a number of cases that my student has gone through. So he's taken all these permutations and done all these cases, and there's no need to stop by and explain every single one. So I'm going to point out a few of these. So this is the first case. So remember I said that I could have a case like this where I have algan, aluminum nitride buffer layer. And then what we can do here is we have this passivation layer here on top. He's made this sapphire substrate thin. So this is going to be our base case right here, case 1A. And then if I take this and I place just a 10 micron thick heat spreading film on top, remember this has low thermal conductivity. What you can see is that this case is this one right here, where the thermal resistance is closer to say 60 meters square, it should be meters square K per watt. And then if I take this and I now put this heat spreading film on top, you can see the dramatic reduction in the thermal resistance just by putting that heat spreading layer there. Now, what happens if I change this to having an aluminum nitride substrate, so high thermal conductivity, you can see that now it drops further down. So the actual case of what we're making now is this case, because it's the easiest one. We start out with commercial aluminum nitride substrates. We can actually play around with this aluminum nitride layer here, make it thicker to help with heat spreading, and then we put a heat spreading film on top, and I'll show you a little bit about that. Okay, so here's another one. Here's one where we just have the sapphire, low thermal conductivity. This is our base case here. We put no passivation layer here on top. And what we do is we have our collaborator just grow a thicker layer. So instead of 2.5 micron aluminum nitride, 50 microns of aluminum nitride here. And you can see the dramatic decrease from here. This one here, we're closer to 60, a 73% decrease in the thermal resistance just by making this layer thicker. One of the issues, as I show this in cartoon form, is that this growth right here is incredibly difficult. The reason why is I start growing the film thicker, a lot of stress, it wants to crack. And so cracking, of course, is no good. And so we have a collaborator, Steve Kahn at the University of South Carolina. He's figured out how to grow really thick layers of aluminum nitride by MOCVD. And so the nice thing about it is that by growing by MOCVD, he actually, so it's metal organic chemical vapor phase deposition. He can actually remove a lot of impurities. He can actually grow these layers tens of microns in thickness. And so when you do this, this is what we found. So this is the chemical analysis, this image right here, the chemical analysis of impurities of commercial aluminum nitride substrates. So that's carbon, oxygen, and silicon. And so when we grew these by MOCVD, we started seeing an order of magnitude drop. or actually 2 orders of magnitude drop in some cases of these impurities. And sometimes they were hitting the detection limits of the system. And so when you look at this, what was really nice is that when we did these measurements, Lucas Lindsay at Oak Ridge National Labs, he had done DFT calculations. And the very first time we took our data and put it on top of the DFT calculations, it matched. And these DFT calculations right here are from Team Fed at Notre Dame. And so 2 different calculations show that this is what you would expect for high purity aluminum nitride. Our experiments follow right on top. There's nothing else in the literature that's ever been measured that shows that. So this is other things from the literature. This is the highest thermal conductivity aluminum nitride that follows the classical behavior of what you'd expect. So it says that, yes, we can grow these materials to the right thickness. We can grow them with high purity thermal conductivity. Here's the another one that I'll quickly show. Again, I talked about putting this transducer layer on top to spread the heat. This is working with Shravanti Chaudhary from Stanford, growing diamond on top of gallium nitride HIMPs and on top of algan that we're doing right now. She's developed a method to really expand the width of these diamond crystals. And so when we've looked at some of our previous diamond work and what we've been doing with her, this actually has extremely high thermal conductivity for even films that are about 1 micron. So we can get these thermal conductivities up to 500 watts per meter K. So remember I said before, you don't have to go to 1,000. So this is getting us a good dielectric material around 500 watts per meter K. And you can see now this thermal boundary resistance range is extremely low. This is stuff that we've measured in previous programs. And so you can see the resistance is extremely low for these kinds of films. So this just kind of points back to the kind of fun that you can have with a number of collaborators trying to take these images of how can we take a material that has a really low thermal conductivity, start integrating these materials to really reduce the overall thermal resistance. So the last part that I want to talk about as I wrap up is we always complained that, or at least I've been complaining that the thermal conductivity of these materials is quite low. Is there something that you can actually do to increase the thermal conductivity? And so there's a concept called digital alloys that I want to talk about now. And so when you typically grow a material like aluminum gallium oxide, it basically has a crystal structure that is the same as like gallium nitride, but you don't necessarily control where all of the aluminum goes inside of the lattice. And so a digital alloy is basically taking a layer of one material, growing it, and a layer of another material, growing it. And so you alternate these. And again, our colleague, Steve Kahn at the University of South Carolina, he can actually grow these in layers in microns of thickness. But most people that have studied this, these superlat structures before, have noticed that whenever you have more interfaces, you typically have something that is more thermally resistant. But I want to show you what we're finding in our research here. There is something, let's see, because of the time, I'm going to skip through some of this. And I'd be happy to come back to this if you have questions. So one of the things that I want to point out is that when I have 2 materials that are put together, typically what we understand is that there's a phonon spectrum or density of states in one material. There's a phonon density of states in the other material. Whenever you put these 2 materials together, there's an interaction between these 2 that's not captured by me calculating what happens in material 1 and material 2. And so this is a neural network potential. This is done with our collaborators, Shake and Henry at MIT, Team Fei Luo at Notre Dame. And so what they did is they predicted that whenever I take silicon and germanium and put them together very locally near this interface, all of a sudden I get this peak that doesn't exist in either the germanium, and it doesn't exist in the silicon. There's a new mode that pops up, the vibrational mode. These vibrational modes help to carry heat. And so what we were able to do was go use basically a TEM that was using SEAL STEM, is EEL's electron energy loss spectroscopy. So what we're able to do is measure these vibrational modes, and we're able to confirm that right here. So this is the interface. So 1 micron away from the interface, you're basically seeing on the silicon side of the interface, you are seeing a peak at 48 MeV, which is 11.6 terahertz. And the calculations were showing somewhere right around 12. So for experiments versus calculations using a neural network potential, that's actually pretty close. And it's showing it's biased to one side of the interface and not the other. So it shows that these interfacial modes can exist. And so here's what a digital alloy looks like, which I think is pretty amazing. So you can see these layers, you can see the atoms here. And when they do the analysis of the TEM, this is grown intentionally, 2 layers of GaN, 1 layer of aluminum nitride, 2 layers of GaN, 1 layer of aluminum nitride. So they can actually put these things down in very high precision. And so what you're seeing is that as you start growing some of these materials, you have very ordered crystal structures versus this unordered one here. So this is aluminum gallium nitride. This is an aluminum gallium nitride digital alloy. And so what we believe is that you will see different modes in this material than you will in this one. And so these are things that we're looking at, especially as you start bringing materials together. So this is the interesting thing. If you have a superlattice structure, this is showing you the gallium nitride thickness. Yeah, I don't have a, I'll show you the picture on the next slide. So the gallium nitride thickness of the half period. So if I have gallium nitride and aluminum nitride, say the total thickness is 10 microns, then my half thickness would be 5. Or if I have, like, say, 1 nanometer of GaN, 3 of aluminum nitride, my half thickness would be 2. And so what it shows is if I do a superlattice, this is out here, but if I do the digital alloys, you can see that the thermal conductivity is rising much faster. So remember before I showed you that when I made these AlGaN structures that the thermal conductivity was below 10. You can see when we start doing these digital alloys, and this is just the first round of tests that we're doing, we're pushing the thermal conductivity up. But then not only are you pushing the thermal conductivity up in terms of what's happening through the thickness, what's also really interesting, and so this is another picture right here, we're actually getting highly, we get high anisotropy where we get heat spreading within the plane. So this is actually a measurement on one that we recently did where the KZ through the thickness was 9.6, but within the plane, this way, it was close to 40. And so this is showing that we can play around with these digital alloy structures, and we believe that we can push the thermal conductivity up as well as increase the thermal conductivity within the plane. That will now build in heat spreading into these ultra-wide bandgap devices. So this is the first time someone has actually gone through and said, how can I build a structure where typically everyone's saying the thermal conductivity is low, and I actually start building these architectures where now I can manipulate the overall thermal conduction through the system. We believe that as you start looking at the closeness of these interfaces, those interfacial modes are actually enhancing the heat transfer. That's just a hypothesis. We still have to go figure that out. But this is sort of what I was trying to get to, that engineering the thermal properties of these materials, either by heat spreading, by adding materials, as I showed you earlier, or by going to digital alloy architectures. This is a very interesting way of starting the process of thermal management. So I'll skip this part as well. So in conclusion, wide bandgap semiconductors, I think they have a lot of promise for the future of RF, as well as power devices. One recent discovery that we've made as well is that we've been able to dope aluminum nitride, P-dope and N-dope. So now we have an ultra-wide bandgap high thermal conductivity material that we can use. That's coming out of our mirroring. However, regardless of the material, the knowledge of the material structure and property relationships, along with thinking about co-design, that will be the key to moving the technology forward. So everything I've shown you here today has been thermal. If you ask me what happens to the electrical properties, no one has actually gone down that path yet. So I will admit that up front. So that's something that needs to be done. The manufacturing technologies for a heterogeneous integration, both how do you grow that diamond to get it really high thermal conductivity in thin layers? How do you do bonding? How do you do all of these things such that you minimize the thermal resistance and you can do it at scale? So doing it on a wafer scale chip in the lab is one thing, but being able to do a wafer scale in a manufacturing environment is another. And then for the future, we'll need to continue to address the concept of digital alloys. It's a very interesting thing that we're discovering here. And I think our mirror only has 1 more year left. And so it is opening up a lot of eyes in terms of how do we continue to manipulate these architectures in order to really push the thermal designs. Then the last thing, I don't want to forget that, yes, that's just the chip. We have to come back with aggressive cooling schemes, architectures, fluid flow, two-phase cooling, all of those things are still needed. But I just wanted to give you an appreciation for the things that you could do inside of the chip before the heat ever reaches the heat sink. So with that, I'd like to thank you for your attention and answer any questions you may have.
Two questions if I may. When it came to the bonding with the ion beam bombardment, are there other, I'm not familiar with the equipment, so are there other beams that use different ions other than argon, with which you could compare the results to see what the effect is?
Yes. Have we done that? No. And so, right now it's like we've stuck with the argon beam. Our collaborators in Japan have used that the most. And, when we're starting out, a lot of these processes, it takes them a little bit of time to work out. So they wanted to continue to use argon. Can you use other materials? I mean, other gases? Yes. What will that do? One of the parts that I skipped is that we've shown that you can actually embed like things like nitrogen and other small atoms in your interfaces, and the thermal conductance goes up as well. So we think that there's some room to play with both the bonding as well as embedding those gases at the interfaces in order to improve things. So a lot of room to still be done there.
And my second question was, is this research more fueled by interest in seeing like the ultimate thermal conductivity that you can achieve, or is it more geared towards providing more powerful but commercial consumer products?
There is, so I would probably say, even going back to gallium nitride, you're seeing gallium nitride in commercial products. The initial drivers were LEDs, so that's the commercial side. But for the RF and power side, at least the RF side, there was a big interest from DoD for communications. And so you're probably seeing a driver from that, but there's still a benefit that would come with 5G, 6G, whatever the next G. And because also, like when you go to higher frequencies, you can make some of these devices smaller. So there's some benefits there. But the major driver in terms of who's paying for the initial research, it oftentimes comes out of DoD. And so I think you'll see broad benefits as we move forward. So the reason why we got into it is because there's one thing that makes it look like if you go to these wider bandgap materials, you can do better, and people are willing to throw up their hands. And it's like, as thermal engineers, we wanted to jump in to see, can we really solve this? And so we tried to make some progress, and I think it's making people think twice now about whether or not it's going to work. There could always be another technology that comes along and scoops it. Like I just mentioned, we developed a way to build aluminum nitride, and so that might, you already have the high thermal conductivity there, so we'll see where that goes.
Thank you.
We have two questions online.
Yes.
The first one is, how long does it take for an acceptable bond to form? The next question is, Carl is asking, is the Veritic MOCVD aluminum nitride C-axis oriented? In other words, does it have good piezoelectric properties?
So second one is C-axis oriented.
C-axis, yes.
Yes, it's C-axis oriented. Haven't measured thermal piezoelectric properties, but it is C-axis oriented. The first one, when you do surface activated bonding, this is actually the same process they use in making SOI wafers. And so you actually place these together and they bond quickly. The wavefront, as you put them together, if you're online, you put them together like this, and the bond front actually moves fairly quickly. The annealing part can be done later. That annealing that we did was for 30 minutes. So, and that was not even optimized, but the initial bond occurs very, very rapidly.
Okay. Any other question from us?
So you showed very interesting data on the digital rods.
Yes.
And just so that I understand this correctly, are you saying that as the periodicity becomes smaller, you get a higher thermal conductivity, or is it when the lattice becomes actually larger that you get a higher?
So, this is interesting. This plot right here was just put together 3 weeks ago. So, and this was because of all the measurements we're making. So I don't know if we have the full understanding of where that peak occurs, but what it's showing is that when you look at the gallium nitride thickness overall, as we increase it in that ratio, that we're seeing this thermal conductivity go up. And so we don't know where it's going.
Separated.
Yeah.
As you increase the separation, that's when
there's going to be something in here where you see how small these are, right? So as you increase this, it's getting better. And then at some point, it's going to look like a super lattice and it's going to turn over and come back down. And so we're not really sure where that point is just yet.
Okay, so yeah, thank you for your exciting work. When you were talking about the device temperature, where is the location of temperature you're talking about?
Awesome.
How usually measure that temperature?
Good. So this is yeah, that's the stuff that I like to do and I left out. So the reason why I say I'm not even asking my PhD students, it came from my group, so I know what you did. I'm kidding. No, seriously, what you do is you typically use Raman thermometry. And so the way we've been doing this, so when you have ultra-wide bandgap materials, you use invisible light, it wants to go straight through, you don't really know what you're measuring. So we typically, and I'm saying this because he and I talk about this a lot as we're developing it, you put a material that's on top of a nanoparticle or a series of nanoparticles that are Raman active. So you know when I receive that Raman signature, it's coming from the top of the device. So we'll use, a sort of a dielectric, you can even use diamond particles on top. And so that's how we do it. We do Raman spectroscopy on the top of the device. So he's measuring somewhere here in the middle of this channel, but the particles are sitting on top.
Yeah, that's great. And how did you expect the value of the thermal boundary resistance or thermal boundary conductance? I think you showed this data, right? So
Not on this one, but on the previous ones.
yeah, previous one, that's why. I think my understanding is that measuring the thermal boundary resistance is not really straightforward in general.
Yeah, so again, for a lot of these, so you're seeing this thick wafer. I mean, a lot of these we're having to then, I'm mentioning it, but I didn't talk about it. You use what's called smart cut, so you get ion implantation here. So you'll implant it to a depth, maybe it's 10 nanometers, 20 nanometers. And so we'll remove it. So we'll have a very thin layer. I think the highest that we've gone to is about 40 nanometers. And so in the beta gallium oxide is fairly resistive. That's why you have to have it fairly thin. And so by using TDTR, it goes through that interface, it goes into the silicon carbide underneath, and we're basically using different frequencies and using that multiple measurements to try to back out the thermal conductivity of this layer as well as the thermal boundary conductance, because we know the thermal conductivity of the silicon carbide.
Rohini?
Great talk. I guess, I mean, as somebody who's kind of external to this, when you talk about the interfaces, especially when you have these interfaces between two different thermal conductivity materials, would you also be concerned about what those interfaces do to thermal expansion at different temperatures? And how much of that also figures into your interface resistance potentially?
So we haven't looked at the thermal expansion. Two things that we're concerned about. One is that when you have these interfaces, say like this, we're worried about mechanical adhesion. One. But the other thing is that as we start designing these interfaces, for certain devices, you have to worry about traps. So the fields can extend down into the substrates, and you don't want to have trap states on top of the device as we grow, say, a diamond layer, or if you have a bond at the bottom, depending on the device architecture. And so we're worried more about the defects that may cause trap states. So we haven't even gotten to that, the thermal expansion cycling. But so working with a collaborator over in England, we have done mechanical, just shear testing to see what force it takes to break those apart.
One question here.
Can you please explain how do you measure the interface phonon energy that you showed was about 12 terahertz?
Yes. So this is called it's called electron energy loss spectroscopy. So to me, it's like I started out doing Raman, so it's similar to Raman. So when you have Raman, you have light that interacts with the surface, and some of the photons will basically interact with the vibrational states of the lattice. And so those photons will lose energy by basically causing a vibration to occur in the lattice. So you could actually measure the loss in the energy of the photon. That's the Raman spectroscopy portion. So the same thing will happen with an electron beam. So the electron beam will actually pass through the sample, and some of those will lose energy because of scattering and other interactions, but some of them will lose it because they cause a phonon vibration in the lattice. And so there's a certain part of the spectrum at which that occurs, and you have to have very specific detectors that can actually measure that. So these are called high resolution energy EEL stem systems. And so there are a few of them that exist. And so we actually did these measurements at UC Irvine. They have a microscopy center, also at Oak Ridge National Laboratory. So we worked with collaborators there that run these systems. We brought our samples, and we could actually measure the loss in energy of those as those electrons pass through in the area where they would actually match up with the phonon vibrational states, because we knew what the phonon vibrational states were in the materials, because we had done the calculation showing that where we thought this might occur. So we looked in those windows, you measure in the silicon germanium, you don't see anything. You measure in the silicon, you don't see anything. As you scan and get closer to the interface, all of a sudden you start seeing these losses occur right there where we did the calculations.
These are cross-sectional samples and you'll-
TM samples are really thin.
Okay, good, thank you. We're running out of time, but one last question online. How does the SL trend for aluminum nitride, gallium nitride compare with the values for other SL systems such as aluminum astatine, gallium astatine, and others?
I don't have that comparison.
Okay,
Yeah, so I apologize. I don't have that comparison for the superlattice compared to the others. I
okay,
think it's just been interesting to see the fact that as we change some of that architecture, that we're actually moving the thermal conductivity in a direction that I'll be honest, a year ago, I didn't think it was going to work. And wasn't sure if it was going to work. So it's interesting now to see if we can go back and make some changes there, but I haven't done comparisons to other
okay,
materials.
that's good. Let's thank the speaker. He has 2 other meetings.